The big question for this segment is, how did our universe get more complex as a result of the first three thresholds of increasing complexity? Okay, now we're ready to go back to the beginning and start telling the story of big history. What I'm going to do in this lecture is to tell the story of the first three thresholds of increasing complexity. But I'm going to tell that story in a very simple way. The first three thresholds of increasing complexity are: 1. The appearance of the universe itself almost 14 billion years ago in the Big Bang. 2. The appearance of the first stars, beginning perhaps 200 million years after the Big Bang. And 3. The creation of new chemical elements inside dying stars, a process that began as soon as the first stars died and continues to the present day. As you study these first three thresholds of increasing complexity, look for how woven through them all are the core concepts of increasing complexity, new energy flows, the Goldilocks conditions that made them possible, and new emergent properties, the new qualities that make these thresholds different. Okay, let's review the first three thresholds. Threshold 1 is the creation of the universe. This is a fantastic question. How did everything come to be? It's the biggest question we can ask. What was there before the Big Bang? Well, the truth is, we don't know. Now, cosmologists love to guess, of course, but the truth is that right now we really don't know the answer to that question. It could be that there was absolutely nothing, zilch, not even time or space. Or it's possible that there was what cosmologists call a multiverse, a vast kind of multi-dimensional space out of which new universes kept appearing, each beginning with its own private Big Bang. So what happened at the beginning of our universe? Well, here's a very, very simple account of what happened. According to Big Bang theory, something appeared. We don't know what it appeared out of. That thing was tinier than an atom. It was staggeringly hot. We're talking trillions of degrees here. And it was expanding incredibly fast. And it contained everything that's in today's universe. A lot happened in the first second. The rate of expansion slowed. Different forms of energy appeared out of this chaos. They include gravity, the force that pulls everything together, electromagnetism, and the strong and weak force. Those hold atomic nuclei together, and they won't play a huge role in our story. Matter also appeared in several forms, including dark matter, which we don't really understand, and atomic matter made of quarks and electrons, and we are made out of atomic matter. The first important date after the Big Bang comes about 400,000 years later. That's almost 500,000 years later. The universe has been expanding and cooling, and it's now cool enough for electrons, which have negative charges, to hitch up with protons that have positive charges. And they form atoms, which are electrically neutral. Now, before that, photons of light couldn't travel freely through the universe because they kept getting tangled up in charged particles. But now they can move freely. So there's this vast release of energy. It's known to astronomers as the cosmic background radiation, the CBR, or sometimes the cosmic microwave background, the CMB. Now, how do we know all of this? After all, it's a very, very strange story, and it's a very strange claim to make that you know what happened 14 billion years ago. Well, there are several very powerful forms of evidence. Perhaps the most powerful of all was the discovery in the 1920s by Edwin Hubble, and you're going to learn a lot more about this later in the course, that the universe seemed to be expanding. No one expected that. But that seemed to mean that at some point in the past, it must have been infinitely small. But most astronomers remained skeptical for several decades, and many continued to argue that the universe was basically, as Newton had argued, infinite and unchanging. What clinched the theory of the Big Bang for most scientists was the discovery in the 1960s of cosmic background radiation. This was energy coming from everywhere in the universe. Now, that was strange. It was not just coming from galaxies or stars, it was even coming from dark areas of the universe. The Big Bang Theory predicted something like this, as we've seen. It predicted that when atoms first formed, there'd be this huge release of energy. And that's what scientists picked up in the 1960s. The rival steady-state theory could not explain this energy. So that's when the Big Bang cosmology story became the standard story of the origins of the universe and accepted by most astronomers and cosmologists. So let's review what's happened as we've crossed this first threshold of increasing complexity. In the new universe, there are huge energy flows. We don't know where they came from. What were the Goldilocks conditions that created this universe? We don't know. We really don't know this. It's possible that in the next 10 or 20 years we'll figure this out, but at the moment we don't know. And what emerged? Well, what emerged was a universe, an entire universe. And the rest of this course is going to tell you the history of that universe. The early universe, in the first few million years after the Big Bang, was very, very simple. There were hydrogen and helium atoms. There were tiny differences in temperature, differences of just a tiny fraction of a degree. The distribution of atoms was very, very smooth, so the universe was very homogeneous. There was energy, there was dark matter, and there was dark energy. That was it. No stars, no planets, no living organisms. With such a simple universe, how can you make more complex things? This is actually a huge problem. The second law of thermodynamics, as we've seen, says that though the total amount of energy in the universe stays the same, it changes its form so it can do less and less work over time. But it takes work to make complex things or to create complex structures. So you might think that the universe ought to be getting simpler and simpler rather than more complex. Here's one possible solution, and it involves gravity. Gravity seems to have been the first driver of increasing complexity. Now, the thing about gravity is it likes to clump things together, it likes to pull things together. And the early universe we've seen was distributed very evenly. So it's as if gravity needed to take everything in the universe and rearrange it and make it clumpier. So think of this early universe. Think of all these huge clouds of hydrogen and helium atoms. Gravity got to work on them and it starts clumping them together. Where they are slightly denser, it makes them even denser. And as they get denser, gravity gets more and more powerful. So it compresses these clouds. And as the clouds get denser, they get hotter, while the rest of the universe was cooling. So suddenly we have a mechanism that's heating up parts of the universe. Now, eventually, these clouds, and you should think of billions and billions of them, got so hot that at the center, atoms started breaking apart once more, and then protons began to fuse together to form helium nuclei. Now, this is exactly what happens in an H-bomb. When you do that, you release huge amounts of energy. And it's that energy that created the first stars, because at the center of each of these clouds, you now have a sort of furnace that's pushing back against gravity. And the balance between gravity and fusion is what forms a star. So we can think of stars as the product of these two opposite forces. Fusion at the center pushing back against gravity, which is trying to smush the star together. And once they get in balance, the star can exist for billions of years. So now there are billions of stars, and the universe as a whole is more complex and more varied. It's no longer homogeneous. We have now huge differences in density. Stars are very, very dense indeed. In temperature, stars are very hot, and also in gravitational energy. The gravitational forces around stars are very powerful indeed. Let's review where we are after threshold 2. Stars, we've seen, represent a new level of complexity. They also generate new energy flows by fusion at the heart of stars. So with stars, we have new flows of energy through the universe, and those flows of energies are going to power life on our planet. What were the Goldilocks conditions for forming stars? Well, that seems to be fairly clear. First is the existence of gravity. That is to say, a force that can't wait to clump everything together. It doesn't like a homogeneous universe. So there were tiny unevennesses in the early universe, and gravity seized on those to clump matter together to eventually form stars. And finally, what emerged that's new? Well, it's very clear what emerged. Stars emerged and galaxies. We have new differences in gravity, in energy, in density. We have new structures. Stars have structures. They have fusion at their center. They have stores of material outside. And they form gravity. And they form galaxies. And galaxies too have structure, as you can see if you have a look at some of the most beautiful astronomical photographs that we have available today. Once stars formed, the universe still consisted mostly of hydrogen and helium atoms. Other elements formed inside dying large stars. Here's how it worked. If a star had lived for long enough, eventually it's burnt out. It's fused all the protons in its center to create helium nuclei. Now at that point, the furnace at the center stops working. The center collapses, gravity takes over, it crushes the star very, very fast, and as it does so it creates extreme temperatures at the center, much higher than the temperatures that had existed before that. Now the temperatures are so high at the center that helium nuclei can start fusing to form other elements such as carbon and nitrogen and oxygen. If the star is big enough, this process can be repeated until the center of the star fills up with iron. It collapses, it expands, it collapses, building new elements, up to iron, which is element 26 in the periodic table. Then, if the star is really huge, it will blow apart in a supernova. A vast explosion, creating temperatures so hot that they forge all the other elements in the periodic table. So once a few large stars have died in supernovae, now we have a universe with more than 90 elements, instead of just the 2 in the early universe. And those elements can combine to form a colossal diversity of different types of materials. So where are we after threshold 3? Well, the universe is clearly more complex, and now it's more complex chemically. That is to say, we now have over 90 different chemical elements. And it's not just that there's a lot more elements. Those elements can all combine in new ways to form a vast range of new materials. What about the energy flows? Well, the energy flows that created chemical complexity all occurred inside dying stars. But chemical complexity also generates new forms of energy. We can call it chemical energy. The energy that's locked up and then released as atoms and molecules combine and break apart. And that energy is going to be crucial for the existence of life on Earth. What were the Goldilocks conditions for the formation of new elements? Well, that's fairly simple. It was the colossal temperatures generated inside dying large stars. Now, it was important that they were large, because the larger the stars, the more powerful gravity is, and that could generate larger temperatures, higher temperatures. And of course, supernovae generated the highest temperatures of all. Those were the Goldilocks conditions. And finally, what emerged? Well, what emerged was a universe that was chemically more complex, in which you now have diverse forms of matter with which you can make a whole range of complex new things. And that will lead us towards our next thresholds of increasing complexity.